Yeah, it's not recording, so you can. Yes.
Yeah,
yes.
sure. All right, welcome to our research lab presentation. We're from the Computer Vision Multimodal Computing Lab, and I'm Sathvik. I'm a rising senior at Liberty High School.
I'm Ashwin. I'm a rising senior at Fremont High School.
I'm Shrihan. I'm a rising senior at the School for the Talented and Gifted.
I'm Justen. I'm a rising sophomore at Ashwin.
And the task that we focused on during this project was the active speaker detection, which is also known as ISD. So what is active speaker detection? It is when you take a video and train a model to detect people talking, even if there's multiple people. Let's just say you take a video of me and Ashwin talking, the model should be able to depict if I'm talking or if he's talking, even if we're talking at the same time. Here's an example of that. You can see while both people talk, the model is able to detect that they're talking based on boundary boxes around their faces. Some of the applications of this include human and robot interactions, social understanding like autism behavior detection, and visual analysis like videos and video summarization.
So to start off the camp, we needed to gain an understanding of how neural networks work and how to use PyTorch, which is the library for the neural network. So we started off with our first assignment using fully connected layers of convolution layers on the fashion MNIST database. So that's a database with 28 by 28 grayscale images of various objects, and the objective, the output, is to classify what the object is. So we tried various sequences of fully connected layers, and the data shown on the table. We found that as the number of layers increased, the accuracy went down. So there could be some overfitting within this model. And then our second assignment was to actually start training models for the active speaker detection task on the AVIR data set. So the first task was to use a fully connected neural network. So the audio and visual encoders were with fully connected layers, as was the detector, and the result gave a best accuracy of 62%. And then the second task, and through the fifth task, was to build a convolutional neural network and to add upon it. So it used pre-trained feature extractors for transfer learning. So the audio encoder was using VGG-ish, which is a pre-trained convolutional network, and the video encoder used VGG-net, and that resulted in a accuracy of 70%. So here's a model of a convolutional neural network. So it has the feature maps with different layers of convolution and pooling, and those lead to a fully connected layer which provides the classification, and then there's the results.
Okay, so after we completed both of those assignments, we transitioned into our own research on transformers. What is a transformer, you may ask? So transformers are deep learning models that are designed for sequential data. So what are the key features of transformers? The first is the attention mechanism. So they focus on different parts of the input sequence, and another part of it is parallel processing. So processing input for faster performance and scalability. So transformers are able to handle larger data sets, and their encoder and decoder architecture is beneficial. We use only the encoder in our study, and another part about it is the sub-attention mechanism, which compares each sequence with each word to determine relevance of the words, and positional encoding, which just adds positional information to understand word order. Here's a model of how a transformer would work.
One of the state-of-the-art models that use transformers for the ASD task is TalkNet. So why did we use TalkNet? We use TalkNet because it analyzes a sequence of the images rather than singular images, giving the input more context. It also uses a transformer-based system with self-attention and cross-attention. And we also use TalkNet because it has a high accuracy on the AVA active speaker dataset with an accuracy of 92.3%. So because we didn't use the AVA active speaker dataset and we used a smaller AVA dataset, we had to fine-tune TalkNet for our data. So before fine-tuning, we had a 78% accuracy But as we started fine-tuning more parts like the detector, self-attention, and cross-attention, we achieved an accuracy of 83%. So here are some of the graphs that we had. So for no fine-tuning, the accuracy steadily increased, but it started at a low 56%. For the only detector training, the accuracy started at 78.2% and kept increasing steadily over the epochs. For the detector and self-attention training, and the detector self-attention and cross-attention training, they start at higher accuracies, but they do start overfitting somewhere in the 25 epochs. So now on to our research proposal.
Okay, so the first step, the first potential improvement for the TalkNet model is POS tagging, which is parts of speech. So as I'm talking, the model would be able to track the words and therefore see if the person is continuing a sentence or if a sentence is ending or beginning. And that could give additional information to the model and allow it to predict with higher accuracy.
Another thing we want to experiment is with LLMs. Large language models are usually pre-trained on huge data sets on the internet, so they come with the advantage of being, presenting data really well. So we want to try to leverage that and see if that could improve the TalkNet model for the ASD task. And we also want to look into reinforcement learning. This is a unique approach that we're trying to take, where instead of looking into a model-based or data-based method of going towards the ASD task, we want to use reinforcement learning, where we use agents and just explore all the different paths and allow the model to create an environment and test out the ASD task and find a better way to, or better solution to the task.
So we also want to look for potential problems to solve. When we were trying to implement transfer learning like VGGH and VGGNet into TalkNet, we realized that while only training the transformer, there wasn't much improvement in accuracy. So what we want to do is figure out what effects the transformer has on these models and see how we can construct better transformers.
Okay, so now the transformer-based models. The first two transformer-based models that we looked at were Hubert and A.B. Hubert. So when looking at the models, we try to find what the key benefits are. So what we learned is the multimodal integration present in A.B. Hubert, which uses audio and visual data and combines them to get better results. Another thing that we learned from both of these models is the self-supervised learning. So that reduces the need for extensive and labeled data sets. Another benefit we noticed with the A.B. Hubert model is that it performs well even though there's background noise or other distractions in the data sets. So improvements we can do for ASD is contextual understanding, so better understanding contextual information, and potential integrations are the audio and visual fusion, so utilize the audio visual fusions of A.B. Hubert in our model, and also experiment with scalability of these needs.
Before I elaborate on reinforcement learning and our approach for it, I want to explain the different terms that are crucial to know so that you understand our approach. First, what is an environment? So an environment could be this room itself, it could be me talking to you, it could be that camera trying to figure out if I'm talking or not. So it's just it's like the place where the model can act upon and then get observations and train and get better as it goes through several epochs. The state is, for example, the number of speakers. It could be the number of audiences in the room. It could be the active speaker detection label. Let's say me trying to speak. And then actions are the things that model can do. For example, the model can say I'm speaking. It can say I'm not speaking, which would be false because I am speaking. And then based on that, we would give rewards to the model, where if the model correctly detects that I'm speaking, I would say, +1, you get candy, keep detecting that I'm speaking when I'm talking. Or if it says I'm not talking, I guess no candy, do better. So that's our basic foundation for reinforcement learning. It's still really foundational. policy-based learning, which we just want to get into. And so our next step for this would be to start training or start building this environment and train it on the Ego 40 data set. What that data set is that data set is a collection of videos of POV, perspective videos of people just walking around in their daily life. We want to use this data set because it emphasizes social interactions, and it's not a big data set compared to the ABA. And so moving on to our current research, we explored 6 different papers. Like Ashwin mentioned, we explored TalkNet and ASD transformers, and like Shrihan mentioned, we explored Hubert, AD Hubert, and 2 additional things that we did were LocoNet and Light ASD, which we will get into in the next few slides.
Yeah, so to understand more about how transformers affect these models, we took the transformer out of TalkNet. So we took the self-attention and cross-attention out, which trains the encoders only. Now, what this showed is a low-high accuracy, and the accuracy was steadily decreasing. So we realized that there might be a problem. So we tried to change the data loader to fix this. So what we did to the data loader is for training, we took random 1-second samples from all the audio and visual data, and for evaluation, we took all the 1-second samples for all that data. And while this method did have a lower accuracy, the accuracy did steadily increase throughout the epochs. Yeah, now in the future, we want to add more fully connected layers into our detector, and we also want to train our models on the larger APA active speaker data set, and add context to the input. So while we were doing transformers for ASD, we also looked into ASD transformers. This utilizes different audio and visual encoders, and has a different use of the transformer using bilinear pooling. Now, we want to use this because it's state-of-the-art with a 93% accuracy. It almost halves the training time compared with other state-of-the-art models, and it has lower flop times. Now, one of the things that ASD transformer uses is saliency maps, and this shows that the main features used in detection. And this shows that the mouth region alone is not the most important part for ASD. It's the full facial region. And the next steps for ASD transformers, we have to finish writing the code. We want to treat it on the larger APA active speaker data set, and we want to compare results when it does have a transformer and when it doesn't.
Okay, so moving on to the structure of Hubert and AD Hubert. Let's start with Hubert. So the key features of Hubert is the mass prediction task. So in the self-supervised training, different parts of the data are masked, and the model is tasked with basically predicting what the person is going to say. So this is done through hidden units, which are clustered through k-means clustering and using raw speech features. So the advantages of using Hubert is improved speech recognition and being able to use transfer learning for downstream tasks such as emotion detection, which can help a lot with context based on how a person's feeling. So if a person is speaking with an angry tone, it's obviously going to predict that a person's going to have to use more aggressive words. And so takeaways for our model is we can implement a self-supervised learning method similar to the mass prediction mechanism to enhance feature learning. And we can also use hidden unit integration to use k-means clustering that will help use learning. Moving on to AB Hubert. AB Hubert extends Hubert by using a multimodal approach that uses both audio and visual data. So the key features of this is the multimodal training. And so the model trains to understand the correlations between audio and visual data. And in the AB Hubert data set, there's enhanced performance, and it significantly performs better when there's background noise, multiple speakers, things like that. So advantages to the AB Hubert model. So it has superior ASD, and it performs outperforms audio-only models, especially in challenging conditions. Visual contextual utilization. So using the visual data to enhance speech recognition and flexibility, the model is able to adapt to tasks beyond just speaker recognition. So takeaways for our model, we can implement a cross-modal approach to use both visual and audio data and find the correlations between those data. And we can also use visual and audio context so so that we were able to better predict what the speaker is going to say.
Okay, moving on to LocoNet. So this one, this paper focused on context. So what context is that it's looking at the same speaker over a period of time, and it's also looking at multiple speakers during that time. So, for example, this model has 3 different parts, where the first part is the encoder, the second part is the long-term intra-speaker modeling. That's where it compares the context between the same speaker over a period of time. The third part is a short-term inter-speaker modeling, where that's where the model would compare multiple speakers. If one person's talking, that means the other person's probably not talking. And then eventually it outputs the predictions. So throughout this process, it starts out with turning the audio and visual inputs into something that the model can read. We call them tensors, which are just an array of numbers that represent the data. And as it goes into the LIM, it uses self-attention to do the context within the speaker over a period of time. Then it compares the audio and visual using cross-attention to get better efficiency in data. And after then, it adds context for between the speakers and then prediction. This method was really efficient, and actually this performed better than TalkNet on the AVA data set, according to their claim on the paper. And like ASD, this paper is most known for not its accuracy, but its computational impact. So for example, the methods they use most focus on the feature extractors. So instead of multiplying just the input with only one convolution layer, it would divide that layer into 2 and then multiply both of them at the same time and combine at the end. That would reduce the computational impact of the model. In fact, it reduced it by like 90% overall compared to other models during the time this paper was published. Another thing is that this model also uses cross-attention to, again, put the audio and visual data together and to get better efficiencies out of it. A new thing that this model introduces is the bidirectional GRU. This kind of model is also used for context where instead of looking at all the data in the video, let's just say we have a 17-second video, it wouldn't look at all of its frames in that 17-second video. It would look at a span, let's just say 2 seconds of that time, and we want to analyze one frame, it would look at that 2 seconds, look at if the speaker's talking throughout that 2 seconds, and eventually come up with a prediction for the frame that we want. So key difference between the transformers and the GRU is that the transformers are able to get context across over a long period of time, but GRUs focus on short term, which can actually be an advantage because we don't want data that's really far away from the point we want to predict from to affect that prediction in that way. Eventually, at the end, there's a fully connected layer that outputs the predictions. And so these are the experiments that we did. Similar to transformers, we wanted to see how impactful the bi-GRUs were. So first, we tested the entire model on the APDIR data set because it's a smaller data set and easier to train on our computers. And in this you can see that compared to with and without bi-GRUs, it didn't really make much of a difference. It was 1% different, 1% higher. But I think this was because we didn't give it enough time to train. These were only trained for 50 epochs, so there could have been a potential for the accuracy to keep going higher as you get into 100 epochs or even higher. And this is an example of a visualization of our model. You can't really hear the lady talking that much, but you can see in the video that whenever she's talking, often it's not being recognized as the person talking, which shows the imperfections or the 40% error in the model that we have. And these are the things that we want to perfect using our research that we've done till now. And that's all the research. Thank you so much for listening.
questions from audience? Probably not about research, anything, or if you want to ask anything, you can also ask here.
So the professor who walked in between, he was the head of this department, Professor Ashwin. I actually ran out to see if I can call him back so I can introduce him properly, but
Yeah, I want to do that too, probably. He just look around,
Yeah.
also to other room. Yeah. Okay, yeah, so we actually did one like internal presentation on Wednesday to ask pretty much a lot of like technical questions. So right now you have been working on this and to get this kind of results. So what will be the exact next step? So let's say now, okay, we'll continue to do the project for additional 1 month, 2 weeks. What do we want to do for the next?
We want to use what we saw from the papers and pick out what worked best and see if we can put together what worked best in a way that gets even more results. For example, we can take the binary switch we already used and test it with the finger adapters from Light ASD.